Alright, exercise 24. This one's pretty neat. We got some kind of interesting examples here. So let's start with the first one. There's probably more examples here, but I tried to go with the simplest ones that I could think of. So, we're gonna let mu. Oh, also we've got some typos in Folland here. I mean, it's not like he's misspelling the word subset, but I mean, it's still things that you should keep in mind. So anyways, let mu n equal delta n. Then what? Then for all f in C0x, we want to show that this goes to 0 vaguely, but not to 0 in norm. So for all f in C0, integral of f d mu n is just f of n, which goes to 0 as n goes to infinity, since f vanishes at infinity. But norm of mu n equals delta n of r, which is, let's see here, is the singleton n in r? Yes, it is, always. So mu n goes to 1, which is not 0. So there's that for B. This is going to be the same one we look at in exercise 25, but let's just go with it. So mu n is this thingy. Then, so basically what's going to happen here is we're going to get, because of continuity, we're going to get cancellation, but if you choose a bounded measurable function with compact support which is not continuous, then you can get you need a jump at 0, and then this will work. So for all f in C0x, by continuity, what do we have? The integral of f d mu n. It's just f of n inverse, n inverse minus f of minus n inverse. And that's, by continuity, we can take those limits inside. And that's f0 minus f0, which is 0. And hence, mu n goes to 0 vaguely. I guess I should have written that in part A, but oh well. Now, let f be the indicator of the compact interval 0 to 1. Then f is bounded and measurable and compactly supported, but for all n and n, integral of f d mu n is f of n inverse minus f of minus n inverse, which is just 1, because n inverse is going to be in this thing, but minus n inverse will not. So integral of f d mu n goes to 1, which is not 0. And so there we go. Oh, I think I'm going to fit everything on here. Hopefully this is readable. Oh, maybe I won't fit it. Oh, we'll see. So here, so this, and this. So let mu n equal delta minus n. Then, this is kind of similar to part A. For this d mu n equals f minus n, which goes to 0 as, I'm just going to write that, goes to 0 as n goes to infinity, because f vanishes at minus infinity. Now let x be any real number. Choose n large enough that the norm of x is strictly less than n, then for all n greater than or equal to n, fn of x equals, let's remember what this equals. This is mu n of minus infinity to x, which is, that's just delta n, no, delta minus n minus infinity to x, which is equal to 1, since we chose n large enough so that right, the norm of x is less than, wait, totally blanking for some reason. Yeah, the norm of x is less than n. Right, so this is certainly going to be in this interval. Or do we want the norm of n, or do we want the norm of x greater than n? Here's what we want. We want, like, x to be here, and then, no, we want, like, we want minus n to be contained in minus infinity to x. So we want, like, x to be here. No, we want, like, x to be here. Oh, wait a minute. Wait a minute. Is this right? I'm getting pretty tired, so I might just be not saying something here. No, that's right, because for n large enough, it's always going to, yeah, okay, so x is over here, and n is over here. So we want the norm of x to be less than, oh, that's what I had before. Okay, we want the norm, okay, yeah, because this picture is backwards because we're in the negative numbers. Yeah, negative numbers are backwards. Lesson of this exercise. So if norm of x is less than n, then this is minus n here. That's going to be like, because if you put minus signs here, then because this is really, we want this to be minus x, and then x is over here, so it's going to be minus n is going to be less than both of these. That's really what's going on here. So yeah, so norm x is less than n. So then for all n, which is greater than n, minus n is to the left of here. So fnx equals the measure of this, which equals delta n this, which means it's 1 if negative n is in this interval. And certainly it is in this interval. Okay. Sorry for that weird confusion, but that happens. Where you get tripped up on a thing that's sometimes easy, but sometimes trips you up. Oh, I actually wrote down here in my notes, had I kept going, I probably would have not messed this up. So, literally in my notes I have this implies that minus n is less than minus x is less than or equal to x. So, fnx goes to 1, which is not 0. Hence, mu n is greater than or equal to 0. Mu n goes to 0 vaguely. Am I still recording? I am still recording, cool. My phone's been weird. But, there exists an x and r such that fn x does not go to 0. And in fact, what we proved here was something a lot stronger, was that every x in R satisfies this condition. So there we go. We finished going through some neat examples. And yeah, that's it.